Welcome, it's Professor Pedrero, and here's a redo of the video for section 5.3, linear independence, because the old mic that I had was just not very good. It was cutting in and out and not very good quality. So let's give this one a try. So our objective is to understand linear independence of vectors and then determine if a set of vectors is linearly independent. Another thing we'll do is compute the Wronskian and use it to determine if functions are linearly independent. So back in section 5.2, we learned about span, and that's to talk about whether we have enough vectors to cover the space using linear combinations. We found out that the vector 1, 1 and 2, 3 do span all of R2 because you can make any vector AB as a linear combination of those two vectors 1, 1 and 2, 3. By adjusting the coefficients 1 and coefficient 2, you can get any vector you want. In fact, let me show you that in a GeoGebra screen here. All right, so here are our u and v vectors, 1, 1, and 2, 3. And if I plot the c vector here and I adjust some of the coefficients, you can see that I can hit all kinds of vectors in our space that we want to make. So in fact, I can make anybody I want. So in fact, we asked if you throw in vector the vector -1, 2, okay, does that harm our span any? And the answer is no, because we even saw this. If I make this coefficient be -7, and this one be 3, then you can see that we can hit that vector, any vector we want. So let's go back to our activity. So we can show that the vectors 1, 1, and 2, 3 do span. The vectors 1, 1, 2, 3, and -1, 2 also span, but they will involve a parameter. So in fact, there's infinitely many different ways to express AB as a linear combination of the three vectors. So what we want to do, in addition to knowing if we have enough vectors to cover the entire space, is check to see if we have any vectors who are redundant or unnecessary. To do this, we check for what we call linear independence. So if the set of vectors are linearly independent, then none of them is unnecessary. If the set of vectors is linearly dependent, then at least one of the vectors is unnecessary because you could make it using a linear combination of the other vectors. So our definition of linear independence is a constant multiple times the first vector plus a constant multiple times the second vector, plus keep going until you get to the last vector, if the only way to make the zero vector is to choose C1, C2, all of the constants to be 0, then the vectors are linearly independent. If there's any way that any choice for C1 or C2 or any of these, if any one of those is not 0, then the vectors are linearly dependent. As a set. Okay. Now, if the set is linearly dependent, we can remove at least one vector and it won't harm our span. So let's just check here if the vectors 1, 1 and 2, 3 are linearly independent. So to do that, we're going to set up our definition. So we need C1 times 1, 1 plus C2 times 2, 3. And we want that to be equal to 0, 0. Now, if we do the arithmetic here, that would be C1, C1 plus 2C2, comma 3C2 equals 0, 0. Or in other words, C1 plus 2C2, comma C1 plus C3C2 is equal to 0, 0. But what that will do is set up for us a linear system. C1 plus C2 equals 0. and 1C1 plus 3C2 equals 0. And if we RREF this matrix, we will get the identity on the left-hand side showing that the only solution is C1 is 0 and C2. Okay. Now, let's check and see if the vectors 1, 1, 2, 3, and negative 1, 2 are linearly independent. Well, we do the exact same thing, set up the same equation. Equals the 0 vector. Now that's going to lead us to, after just a little bit of work, a matrix that looks like this, which if I RREF, I will get 1, 0, negative 7, 0, 1, 3. So that tells me that I'm going to need a parameter. And if I let C3 be t, then C2 will be negative 3t, and C1 will be positive 7t. And if I let t equal 1, let me slide this up so it's a little easier to see, then 7 times the 1, 1 vector minus 3 times the 2, 3 vector plus 1 times the negative 1, 2 vector does make the 0 vector 0, 0. What this does is it allows us to, so we know this set of vectors is linearly dependent. Let me write that out. Okay. So since it's linearly dependent, we can solve for one of the vectors in terms of the others. So for example, I could solve for the vector 1, 1 in terms of the other guys. If I move these guys to the other side and then divide by 7, the vector 1, 1 is 3/7 times 2, 3 minus 1/7 times negative 1, 2. Okay. So that tells me that I could get everything with the vectors 2, 3 and negative 1, 2, and the 1, 1 vector could be thought of as unnecessary. Similarly, we could solve for, let's say, this guy right here, the negative 1, 2. So negative 1, 2 vector is equal to negative 7 times the 1, 1 vector plus 3 times the 2, 3 vector, meaning that negative 1, 2 can be achieved using these two vectors, so he doesn't contribute anything new. And finally, the vector 2, 3 could be thought of as, if I move him to the other side and divide by 3, 7/3 times the 1, 1 vector plus 1/3 times the negative 1, 2 vector. So the 2, 3 vector could be thought of as unnecessary because I can get anything that I could make with him, I could have made with the other two vectors as well. So what I'm going to do is have you pick any two other vectors in R2 and then check to see if those two vectors are linearly independent or not, and convince me right here. And we'll pause there for this video.